Hello, everyone, and welcome to today's webinar, Battery Cell Selection Using AboutEnergy's Cell Database with TAITherm. My name is Chris Niva, Marketing Operations Coordinator at ThermoAnalytics and host of today's webinar. Our presenters today are Dr. Gavin White and Dr. Zachary Edel. Gavin is the co-founder and CEO of AboutEnergy. And prior to this, he completed his PhD at Imperial College London, where he developed novel methods for measuring the thermal properties of lithium-ion cells. Gavin has combined this expertise with that of his co-founders to create AboutEnergy, a one-stop shop for advanced battery modeling. The goal for AboutEnergy is to make battery development as simple and efficient as possible using their advanced software platform. Zach is a senior research engineer at ThermoAnalytics, feature owner for the TAITherm battery extension, and a subject matter expert for vehicle electrification modeling. He has many years of research experience developing advanced physics models, performing numerical modeling, and performing experimentation and data analysis. He has worked with various OEMs and Tier 1 suppliers to model battery degradation and BMS design, with a focus on optimizing BMS control strategy. Zach received his PhD in mechanical engineering at Michigan Technological University in 2013. Throughout today's presentation, you may submit questions in the questions box, which we will review at the end. And we're also recording this webinar, and we'll be sending you the link following today's presentation. And with that, Zach, if you're ready, you may begin.
Okay, thanks, Chris. So today we'll talk a little bit about an introduction, and then Gavin will present the AboutEnergy's Volt database. I'll talk about the TAITherm thermal electric model that we use to compare different cells, present the combined simulation results, and go through some conclusions. So with that, I'll turn it over to Gavin.
Yes, thank you very much, Zach. I'm just going to share a screen. There we go. So yes, today I'm going to tell you about our new software platform called the Volt. So my name's Gavin. I'm the CEO and co-founder of AboutEnergy. And our goal at AboutEnergy is to make battery development as simple as possible and really accelerate electrification. So how we do this is through our new web platform called the Volt, which is a database of lots of different commercially available cells, which I'll tell you more about in a second. So first off, we want to start with what the Volt can be used for. And primarily it is designed to help people select cells, to optimize their system, to benchmark different cells against each other, and also to share battery data securely. We really see the Volt being your virtual lab, a place in which you can run experiments virtually rather than having to do them through lots of very expensive and time-consuming physical experiments. There are many barriers to battery innovation, and a lot of these revolve around the requirement for very large facilities that can be very expensive, as well as the very scarce pool of battery scientists. There's a huge skill shortage in the industry, and even if companies wanted to centralize all of this today, there isn't the pool of talent to do this. And it's also extremely difficult to do. Huge amounts of research go into this, and there's a lot more to do in order to simulate batteries effectively. We do this by bringing together lots of leading research in the UK. We're a spin-out company from Imperial College London and the University of Birmingham, but we've already worked with all of these universities on the screen, and we're in talks with many more. And our idea is to try and pool research from leading universities and bring that together into provide a useful service. And we're already speaking with universities in Europe and the US to expand this further. And how we do this, there's a few different areas of expertise we have. One is our thermal control, which allows us to control the temperature of batteries really accurately using a Peltier PID system, which leads to really accurate data. We also have developed, over the course of decades at these universities, leading cycling protocols, so how to charge and discharge the battery effectively in order to take them accurate measurements. And we have a lot of expertise in how to tear down a cell in order to build very representative half cells and 3 electrode cells, which allows us to build the most advanced models. And that flows on into modeling. So how do you take all this experimental data and build that into a simulation tool that best represents the battery? Our approach is white box, and what we mean by white box is that we allow our customers to see all of the input numbers and to see how the model works. And that's really useful because it gives you more assurance over what model is being used, but also it allows you to tailor it. You can add elements to it and customize it for your application. We take a very research-orientated approach, which is very honest. Batteries are extremely complicated, and taking these measurements is very, very difficult. So we're always honest and upfront about how we've managed to do it and what the sort of certainties and uncertainties are on certain parameters, so that you can use these tools with full peace of mind. And our approach is platform agnostic. We want to build our tools so they work in any platform. And today you're going to see exactly how you can use our models in the Thermoanalytics TAITherm platform. So now let's have a look inside the Vault. So the Vault is this huge database of lots of different cells. You can see here there's actually 511 cells listed from lots of different sites. So you can see a range of manufacturers from LG, Molicel, Samsung, etc. And here we're providing lots of high-level information on the cells. So this is often taken from cell data sheets and scraped from the internet. They can be sorted by manufacturer, and there's many, many different columns that you can kind of view and sort and filter from at a very high level. And the goal here is to basically summarize all the different cells. And if you look at, say, even one manufacturer like Samsung, there's 38 different cylindrical models on the market alone from Samsung. So it's a very, very complex process to choose from. And we have this verified column, which is basically us working our way through each cell and actually collecting the data sheet for that cell and testing it to basically say that, you know, the data supplied on the platform has been verified by us as being accurate and true. So next, going a bit deeper, we're going to look at the advanced data sheet, which supplies more information on the cells. So this is when we buy the cells and we provide that information. So here we're going to show the AboutEnergy Gen 1 demo cell, which is basically a demonstrator. It allows us to show all the parameters we could measure for other cells and what they look like. So this includes things like chemistry. So in black, you can see the information we scraped from data sheets, and in green, the information that we've actually measured ourselves. So we can provide more resolution, not just NMC, but NMC 811. Then looking at the geometry of the cell, the thermal properties, all the different properties you need in order to start to engineer a system around them cells. We also provide engineering drawings for that mechanical design and CT scans, so you can see actually what's the components of the cell, and we use these scans to help us build the most accurate models. And finally, we do material composition as well. So we actually measure what materials are in the cells, and with partners, we can work out the supply chain for that. So now we'll look at data, and we supply data for the cell. So here you can see examples of capacity loss over a number of cycles for this demonstration cell. But we also want to provide things like rate capability, viewing that over lots of different cycles, so you can see at different currents, how that cell would perform. And also looking at state of health, not just capacity loss, but looking at what type of capacity loss was it? Was it loss of lithium inventory or loss of active material? So now we'll have a look at battery models. So if we go into that demo cell again and we actually go into models, we have two types of models. There's equivalent circuit models and physics-based. So on equivalent circuit models here, you can see that you can basically configure what type of equivalent circuit model it is, choose the platform you want. So here it's showing selecting TAITherm, and then you can actually hit download, and you can download that specific cell in the platform that you like. And now looking over at physics-based models, so we're thinking of DFN, so the Doyle-Fuller-Newman model, the single particle model with and without electrolyte. Again, configuring that model, what type of thermal model and network model you like, and then download that in the platform you like, whether that's, say, the battery parameter exchange, open file format, or if that's PyBAM, the open source modeling platform. And today we have collected data for over 35 cells for equivalent circuit models, and we're building lots of different types of equivalent circuit models. There's the standard lumped ones, but looking also at the more complex 3D ones, which can be utilized in the thermal analytics platforms, and then all the different platforms that we support. So whether you want to download the inputs for their models as a CSV file, or just download that straight into the thermal analytics platform. So really key features with our equivalent circuit models, we try and make them as user-friendly as possible. So they're as simple to use as required. They're white box, as I said before, so you can see all the parameters, you can see the CSV lookup tables, and you can edit them how you like. And we do all of this in-house, so it's all in-house parameterization. And coming soon, we plan to add more platforms. We plan to add things so that you can generate packs much quicker rather than having to like drag and drop many times over. We want to make our ECM lookup tables compatible with standard off-the-shelf BMS chips from, say, Texas Instruments. And yeah, continuously improve our experimental techniques and the parameterization process to make the models more accurate. And obviously, we want to add more cells, so collecting more information for more cells and even more on top of that. So how we deliver this is through a subscription package for which there's different tiers. So there's Enter, Explore, and Elevate. And these are all positioned to different areas of the market for different stakeholders. So if we look at the development process, so the whole way from developing materials to manufacturing electrodes, then building that into a cell, taking them cells, designing a pack or a module, then controlling that module with a battery management system, as well as then predicting the lifetime of that cell and second life and recycling. So the different packages are really focused on different areas of this chain. So Enter is for the pack designers and system integrators. Explore is more focused on the cell manufacturers and electrode manufacturers. And Elevate is really the enterprise solution for very advanced customers in any of these segments. And these different packages come with different levels of support. So looking at Enter, you kind of get the equivalent circuit models and thermal. Explore unlocks the electrochemical models, so the Doyle-Fluor-Newman, the single particle model for them different cells. And then Elevate also includes degradation models for themselves, as well as enterprise level bespoke solutions. And this platform is continuously improving. So we're always adding more cells and new products very quickly. So that's the presentation on the Vault and how the AboutEnergy database can be used to kind of benchmark and select cells very quickly. And now you're going to see a presentation from Zach on how to use the Vault to actually design a system. So thank you very much.
Thanks, Gavin. So for the next engineering design study, we've taken 5 unique battery types from the Volt to determine the difference in performance using simulation. And we're using different operating scenarios, including constant current discharge at a nominal 1C rate, drive cycles from the IEEE database. Heat sources include the battery cells and bus bars, and there's a heat exchanger with the input temperature taken from measurement. For the thermal model setup, we have a TAITherm 3D thermal model, which contains 444 cells split into 6 sets. So that's a 74P6S topology. We have fluid streams that are used to model cooling of the pack in the cooling ribbon shown in brown. And we have Joule heating applied to the bus bar geometry shown in green. The battery setup is specified in TAITherm. The inputs are defined in the integrated battery setup GUI in TAITherm, and the battery config.txt file comes from the Volt database. There are 2 inputs that define the electrical setup and cell specifics of the particular battery shown here. For the Joule heating setup, we have a thermal model, which includes geometry for the bus bars. It's a continuous geometry with thermal boundary conditions, initial conditions, and certain electrical parameters such as curves. And then the electrical setup file defines the electrical parts, boundary conditions, electrical attributes, and contact heating attributes. So for the constant current discharge study, we've imposed a pack current of minus 370 amps, starting at full charge and going until a cutoff voltage of 2.5 volts. So the models are all run until that cutoff voltage is reached. And we have the cooling rig with fluid streams, the joule heating in the bus bar geometry, and the battery heating in the cell geometry included in the same model. Looking at results from our 5 different battery cells, we can see that they reach full discharge at different times and different depths of nominal depths of discharge based on the voltage differences from the simulation. So the simulation ends at the 2.5 volt cutoff, and based on the voltage at 1C, we can see when those cells stop discharging. And that's a function of C rate or current applied to the pack. So at different current rates, you'll see different cell capacities. We can also look at temperature gradients within a cell and maximum temperatures in the cells as well to compare against design constraints. Here we have animations of the full pack. So what we see initially is that the heating on the bus bars is non-uniform based on where the current is flowing into and out of the cells that are connected in parallel. We can also see that the fluid streams heat up as they flow through the pack, starting at 20 degrees Celsius and heating up to several degrees warmer at the pack outlet. If we look at the cell temperatures, we can see the influence of those heating factors and cooling factors on the cell temperatures compared for the different cells in the pack. So some cells are getting warmer due to the joule heating of the bus bars connected to the cells on top and bottom, and some cells are getting warmer from the heat up of the fluid stream as it flows through the pack. We can also look at just the highest temperatures in the pack and compare the maximum temperatures of the cells against each other. There's some obvious differences here, a few degrees Celsius. This may or may not be significant depending on your design considerations. And of course, this can be compensated for with different cooling system designs and boundary conditions. Looking at joule heating, we can see the imposed heat on the bus bars. This is constant during the simulation because we have a constant current, but for a drive cycle that's changing. And this is a full finite volume simulation with element level heat rates. Comparing different cells against each other, the first thing we looked at was maximum cell temperature. And in the dotted line, we've assumed a nominal maximum cell temperature limit to eliminate certain cells from the feasible ones. And from this, we can see the best temperature is the Samsung 50S, and the Samsung 50E is above our artificial limit. Looking at usable capacity from the constant current discharge test, we can see that the LG M50L does the best. The Lishen LR21700 SF does the worst. And of course, we want to maximize usable capacity. So this has to be balanced against other factors. Looking at pack weight, we can see that the LG M50L is the second lowest. The Samsung 48X is the lowest. And we can see cost per cell, how those compare as well. And in that case, the Samsung 48X is also the best. So there's a lot of different design parameters to consider here. So to help narrow down that selection, we've created a design matrix where we've ranked each cell based on the maximum cell temperature, usable capacity, weight, and cost. And then we've come up with weighting factors for each one of those design constraints. And when you multiply those together and add them up, we can see that the LGM50L is the best cell for this pack. You can also look at variable temperature and current. So the battery configuration parameters from the volt database are temperature dependent. So the amount of capacity that you're going to get out of a pack depends on the temperature at which the pack is cycled at. And you can also look at drive cycles. So in this case, we've downloaded a drive cycle from the IEEE database. We have a continuously varying current and initial depth of discharge of 0.29. This was measured in an electric vehicle, and it had full controls from the vehicle BMS and HVAC control system. So the heat exchanger temperature varied over time, and we've taken that heat exchanger temperature and applied it as an inlet boundary condition to the fluid streams in the cooling rig. Since the battery pack in the vehicle was a different total capacity than the pack that we're looking at, we scaled the current so that the state of charge in an individual cell was the same. And looking at drive cycle results, we can see the imposed heat in this animation, both from joule heating in the bus bars and from the battery heating on the cells. And then we can also look at temperatures, including the mean temperature of the battery cells in the pack over time, as well as the maximum and minimum temperatures. And comparing the maximum and minimum temperatures in one cell, we can see some interesting results. In the top plot, we're showing the exterior temperature results of a single cell. We can see that those depend on time. And on the bottom plot, we can see both the exterior and interior temperature results from the heat up of the jelly roll inside the cell. And we're looking at the maximum temperature inside compared to the temperature on the exterior of the cell. So from this, we can see that at certain points in time, the temperature gradient is as high as about 5 degrees Celsius. And then at other points in time, it's as low as 0 degrees Celsius. So this makes a case for transient simulation, because in this case, if we were looking at a steady state simulation, we wouldn't see much temperature gradient in that cell. Whereas with the transient simulation, with the changing boundary conditions of the heat exchanger temperature and the thermal mass of the cells, we see very significant temperature gradients in that cell through parts of the transient simulation. And then looking at next steps, we can assemble these cell modules into a pack, put those into a full vehicle model, and look at how the temperatures, state of charge, and currents vary throughout the entire pack based on the local depths of discharge and local temperature distributions and heat rates. And we can also look at things like solar loading on the vehicle exterior. We can look at CFD in the cabin of the vehicle, how that influences the comfort of the passengers, and how the control of that HVAC system influences overall range, and how we need to control the battery pack to maintain temperatures given those loads in a transient 3D thermal analysis. So in conclusion, AboutEnergy's Volt database can be used with TAITherm to aid in the selection of battery cells from over 400 commercially available alternatives. Those models can include thermal properties and are available in equivalent circuit models, split equivalent circuit models, single particle models, and Doyle-Fuller-Newman models. And we've shown that a 3D thermal electric battery pack model aids in the selection of cells, and that prediction is improved by considering 1D fluid streams in ribbon coolers, joule heating in bus bars, and cell balancing in the electrical equations. From that analysis, we see that the LG M50L was chosen as the cell of choice for this application due to the highest usable capacity, moderate weight, and reasonable price. And we will be presenting these results with more detail at upcoming conferences such as the SAE TMSS conference. And we'll be continuing this work with About Energy going forward and advancing our capabilities in a joint effort. So you can get in touch with About Energy using these links. And if you want to get in touch with me, you can email me directly or go to our website. And there are several forms of communicating through the website as well.
All right, thanks, Zach. Thank you, Gavin. At this point, we'll go ahead and open it up for questions. Let's see, first question, what are the advantages of the approach shown here over CFD, and can I couple TAITherm with CFD if needed?
Yeah, so the advantages here are the speed of the simulation. You can run full transient simulations with reasonable run times and still get 3D thermal results and look at temperatures inside cells and outside cells, apply boundary conditions as curves, and look at reduced order convection settings like fluid streams or correlations in terms of like pipe flow and things like that that are built into TAITherm. And if you do want more fidelity, we do couple with CFD very often. And we do like a pseudo transient coupling where we run TAITherm for the transient side and run CFD at intermittent points and couple those two together to exchange fluid temperatures and heat transfer coefficients.
All right, thank you. How are you modeling the geometry of the jelly roll and core?
So in this case, we have a shell part for the battery cell. So the jelly roll is explicitly modeled inside the battery and connected to the case with thermal links. And that jelly roll is comprised of shell elements that have multiple layers throughout them. So it has several nodes through the thickness of the elements. And then we have anisotropic conduction in that cell to account for the difference in conduction through the layers of the jelly roll and along the faces of the electrodes.
All right, thank you. What other battery modeling capabilities are available from Thermoanalytics?
We have a thermal runaway model that we're using along with the CFD venting model to predict the propagation of thermal runaway in the pack and the effect on the surrounding vehicle geometry. We also have a battery lifetime model, and we do have some electrochemical cell modeling capabilities through PyBAM's open source library.
All right, how mature is Volt's database on, hang on, need to expand. How mature is Volt's database on aging factors for the verified cells?
Yeah, for sure. So that's something that we're working through at the moment. We're prioritizing cells that customers are interested in. So there's only a limited selection of them. So I would say if you're interested in the aging parameters, reach out and then we can discuss that further.
Thank you. What are the ongoing research efforts around batteries and electrification at Thermoanalytics and About Energy?
So at Thermoanalytics, we're looking at coupling with 1D system tools for electrified vehicles such as EVs and hybrids, cabin energy consumption, the impact on range, the impact on comfort on the people in the cabin, and then also reduced order battery modeling and onboard model-based controls. Those are some of the ongoing efforts that we're undergoing right now.
And About Energy, the big efforts are going to increase the size of our library. So testing more and more cells, making the models more and more accurate. So both the equivalent circuit models and the electrochemical models. And yeah, finally, the third one is degradation. So we just won a £1 million project with the UK government to develop degradation models with Imperial College London. So that's going to be hopefully a lot of research we can kind of pipe into the platform.
runaway solution.
Sorry, Chris, I think that cut out.
Oh, sorry. Are there any webinars on the runaway solution?
So I think we have a webinar coming up in June on thermal runaway.
Okay. Well, yeah, so go ahead and keep an eye out for the June webinar on that. Looks like that's all we have for questions. So again, thank you so very much, Gavin. Thank you, Zach. That will complete today's webinar. We appreciate everyone for attending. You will receive a follow-up email later on today containing links to download the presentation slides and watch the recorded webinar session. Again, thanks everyone and have a nice day.
Yes, thank you, Chris. Thank you, Zach.
Thanks.